Here is another question from Reddit. You know, I like these questions because I look through Reddit and I see what's there, and if it's something that I've seen other students ask in real life, and then I think, well, if people in real life ask it, people online ask it, it's a good question to ask. Okay, so this is a question from Pink Notes. Pink Notes. I know the answer is no, but why? If the acceleration of gravity at a point is g equals 9.81 meters per second squared, and an object is resting on the ground at this point, is this object accelerating at a rate of 9.8 meters per second squared? Common sense tells me the answer is no, but I can't figure out why. It's a good question, right? And it has to do with the problem the way the textbooks are. So let's start with a block. That's actually a Lego block. And so if it's sitting there, then yeah, the acceleration is 0. If I take it right here and let go, then it falls. We're looking at it from the top, and it has a non-zero acceleration. So let's start with the block like this. Here's the ground, and then here's my block. It's not a very good block. Okay. So if the block is just sitting there, then I know that the acceleration is 0, right? We define acceleration in 2 dimensions as the change in velocity with respect to time. But the velocity is 0, and it stays 0. So this would be the 0 velocity minus 0 velocity over 0.01 seconds or whatever, and that's 0 meters per second squared. So yeah, the acceleration is indeed 0. That's a vector. Now, we can use this with Newton's second law. Newton's second law says that the net force is equal to mass times acceleration. So if the acceleration is 0, and it doesn't matter what the mass is, then the net force has to be 0. If I write this in the y direction, F net y equals may equals 0, the scalar value 0. Meters per second squared, no, newtons, times kilograms, which is a newton. So I know that the net force has to be 0, but I also know that there's a downward gravitational force pulling on it. So that means there has to be an upward gravitational force pulling on it. So we have the downward gravitational force near the surface of the Earth. We write that as mg. And the upward force would be the force from the table. We call that the normal force. And then in the y direction, I can say n minus mg equals 0. So yes, it has 0 acceleration, and it does have g. Now, if I let it go, and so it's in the air, then it's no longer in contact with the table, so there's a downward gravitational force, mg. And in the y direction, I could say F net y equals negative mg. That's the y component of this downward force. That's a g, and I'm terrible handwriting. And that's going to equal to the mass times acceleration in the y direction. In this case, the mass cancels, which is kind of cool. And I get negative g equals ay. So the y acceleration is negative g, negative 9.8 meters per second squared. So the problem comes about with what we call g. So let's switch over here. So a lot of textbooks say g equals 9.81 meters per second squared, and it's the acceleration. Most of them do this due to gravity. But it's not. There is a gravitational force acting on this, and it is not accelerating. So it should be the acceleration due to gravity of a free-falling object. So if there's no other forces on it, then it's acceleration due to gravity. A better term would be to say this. I'm going to even do a better one. G equals 9.81 newtons per kilogram, and that's I'll call it this, the gravitational field. So it's the force per unit mass, and we use the symbol G for that. This is a better way, and I should say that a newton per kilogram, 1 newton per kilogram, is equal to 1 meter per second squared. So the units are the same, the value is the same. It's just what you call it. I don't think this is a good thing to call it. I think this is a good thing to call it. the gravitational field is 9.81 newtons per kilogram. Now, there's an even better way to write this, and it's best to write it like this. G equals 0, negative 9.81, 0 newtons per kilogram. This writes the gravitational field vector, assuming that this is the x-plane and the y-axis is going up, and then z would be out of the page, but that's fine. So here I have a 0x component, a negative y component, and a 0z component, newtons per kilogram. And then if I want to write the magnitude of that vector, I could write that as the magnitude of g. We could also just call that g, and that would be the 0 squared plus this squared plus that squared square rooted, so let's get 9.81 newtons per kilogram. And that is g, the gravitational field. Okay, and that's another small point. You know, we don't write g equals negative 9.81 newtons per kilogram. G is a gravitational field vector, so it does have a direction. But if I just write the scalar version of it, then I don't want to put a negative sign there because it doesn't really make sense. If you wrote gy, the y component is negative 9.8, but just g in general is 9.8. And so this comes up sometimes in the kinematic equations. If you want to make sure that you put the acceleration as negative g. So it would look like this. One of the kinematic equations looks like this. Y final equals y initial plus vy initial t minus 1/2 gt squared. So this is the acceleration is negative g, right? So don't put plus g and then use g as the 9.8. One, physicists might not think you're cool. Two, you're going to get yourself into trouble later, okay? Because it's best to write it like this. I'm sorry, like this is the best way. Right there. Technically, we can even use this is the gravitational field on the surface of the Earth, near the surface of the Earth. Technically, if you start looking at a better model for gravity, let's say even for the gravitational force of the Earth, then I have, here's the Earth, here's the radius of the Earth, it has a mass, me. So if I'm over here and I have some small object, some test mass m, then the gravitational force Fg, I'll write this the full way, it's going to be negative g m me over r squared r hat. So r is the vector from the center of the Earth to the mass. And so r hat is a unit vector in that direction, and that's the magnitude of that vector. And that's not the point I want to get to. The point I want to get to is if I could say g equals Fg over m equals negative g mass of the Earth over, and I'll write it like this, r squared r hat. So I can actually find the gravitational field anywhere due to the Earth using the same symbol. If you put in the r as the radius of the Earth, then you get 9.8. It's pretty close. You might get a little bit of mistake, but that's the same way to write the gravitational field. And the other nice thing about the gravitational field this way is if I look at an electric charge and I put a little test charge, this is Q, and I put a little test charge QT for the test right there, I can calculate the electric force Fe, where Fe is 1 over 4 pi epsilon naught QT over the magnitude of r squared r hat, that's r. And then if I divide the force by that test charge QT, I get the electric field, E, equals Fe over QT. So it's the same, it really matches up well with the way you do things in the second semester of physics dealing with the electric field. And we do the same thing with the gravitational field, and the models look the same anyway. So there you go. That hopefully answers your question. Yes, it's not, you're correct, it's not accelerating, and it does have a gravitational force on it. There is a g there, and all of these problems can be solved if you just don't call it the acceleration due to gravity. It's the gravitational field. Okay, I hope that helps.